So this is the video for section 3.2, and section 3.2 is just a one-day section, so we'll go through all the content in a day. So if you get your 3.2 notes out, we'll start jumping into this. So we have the world's longest piecewise function at the back of the room, and if you in class we were asking where it is differentiable. And so the patterns that we noticed is that the derivative values had to match, and we had to have a continuous function at that location. So we'll go over what that means in terms of the characteristics. In other words, how that function looks. So really 3.2 is we're talking about differentiability. In other words, the ability to find, so you can see the word ability here, the ability to differentiate. Or in other words, the ability to find a derivative. And so first we're going to kind of look at the opposite of that. So the essential question is, when does the derivative fail to exist? In other words, when can we not find a derivative? Well, if we can find a derivative, if you look at this first sentence here, it says to be differential, a function must be continuous and smooth. So in other words, to be differential means to find a derivative, the function must be continuous. So in other words, you should not be lifting your pencil. And smooth. So we should be having a smooth transition from one point to the next as we draw it. And that means, so if we think about the opposite of smooth, there can't be any sharp corners or jagged pieces or anything like that. So let's take a look at some functions that have those jagged edges, so to speak. So the first function we're going to look at is absolute value. It's got a corner right here, and so if we notice when we're drawing this, we can draw it without lifting our pencil. So we meet the continuity requirement, but this point right here is where two different slopes come together. So that point, in this case it's x equals 0, that point right there, we have a point of non-differentiability. So that's a long word, non-differentiability. So non means not. Differentiability means differentiable. So we cannot find a derivative at that location. And when we have two linear pieces coming together, we call that a corner. Similarly, we also have functions that come together, but these functions aren't linear, they're curved. And a good example of that is a fractional exponent. So if you think about this, this is the cubed root, because we have the 3's in the denominator, the cubed root of x squared. And it comes to a point when x is equal to 0 and then comes back up like this. And so again, we have two different slopes coming together. So this would be a point of non-differentiability. In other words, a point where we cannot define the derivative. But since we come together with a curve instead of a line, we call that a cusp. So the distinguishing terminology here is, if I have two lines coming together, we call it a corner. If I have a curve, then we have a cusp. The next function looks like this, and this function is like this is x to the 1/3 power. So if we kind of compare the cusp and the vertical tangent, this is x to the 2/3. So the 2 is squaring everything and keeping it positive. This is x to the 1/3. So we can have negative values and take the cubed root. So this has a negative portion and a positive portion. So it's just that this isn't flipped upward. And so if you notice, this looks like, okay, I can draw this without lifting my pencil. So it meets the continuity criteria, and it even looks smooth throughout this entire domain. And you're right, it is smooth through the entire domain. So the question is why can't we have a derivative here? And really the answer is, this is the kind of the trickiest one, I think. The answer is the tangent line here is vertical. And so if we think about a vertical line and the value for slope, vertical lines have infinite slope. Or we could also say that this vertical line has its slope does not exist because its value is infinity. So by definition then, since I'm saying slope, you're thinking derivative. If the slope can't be, if the slope is infinite, or if the slope doesn't exist, then the derivative doesn't exist either, because derivative and slope mean essentially the same thing. So this fails, the vertical tangent fails from a value standpoint, not necessarily from a jagged edge standpoint. We just don't have a value that's finite. So we say that that we don't have a derivative then at this location where this tangent goes vertical. And then the last one is when we have a piecewise function and we don't even meet the continuity criteria in the first place. So if you notice, just kind of reviewing all four of these, the corner, the cusp, and the vertical tangent are all continuous. You don't have to lift your pencil. But once we lift our pencil, once we have a discontinuous function, and piecewise functions are good examples of those things, then if we lose continuity, we're out of luck. We can't find a derivative at that discontinuity location. So these are the four types of situations where we cannot find a derivative. So I guess the flip side to that is if we don't have one of these four situations, we can find a derivative. So we're going to do just a little refresher here of finding numerical derivatives on our calculator. So we know that if we would do this by hand, we'd have to do the limit method. And we've done the limit method on x squared several times. So that wouldn't be too much of a stretch for us. But we also can find numeric derivatives as long as we know where we want them. We also can find numeric derivatives on our calculator. So just a quick review. We have the functions x squared. We want to calculate derivative when x equals 0 and also when x equals 3. And we're going to do that from our calculator screen, and we're going to use our Math 8 button. So if we get to our calculator screen and we type in Math 8, we get something that looks like this if you have a newer calculator, or something that looks like this and deriv if you have an older calculator. And then we type in, let's go over the newer calculator first. This is for the newer TI-84s. So we do a Math 8, this pops up. This is the Leibniz notation. Remember d dx, kind of looks like a fraction. So we put in our variable x using our variable key. Then we'll hop over here and put in our function x squared. And then this is already here. Oh, I'm sorry, it's not. We have to put in our variable x here. We have to tell the calculator what variable we want to differentiate it. In other words, what variable the calculator will see in the function. And then we put in the value. We want to evaluate it at x equals 0. If you're using an older calculator, it's not as pretty looking. But the syntax, in other words, the order in which you put things in, has to be function, comma, this x stands for the differential x, so it's the dx in the bottom, so that's your dx, and then comma 0 because we want to evaluate the value at 0. So we know, and if we would come up into this space and kind of draw, so I'm using my pointer here, here's my axes, here's my parabola coming down. We know that when x is equal to 0, we're at the vertex, and we also know that the slope of the tangent line at the vertex is horizontal, which means its value is 0. So we know that when we hit enter here, when evaluating the derivative at 0, we're going to get 0 for that answer. So now let's try a location. So really this whole thing, evaluating the derivative at 0 for this function, is just to check to make sure you're putting it in correctly. Now let's evaluate the derivative at 3. So I'm going to go up here and draw in this space again. Here's my axes. Here's my x squared. 3 is somewhere out here, so we have this upward sloping portion of the parabola. So we're going to have some sort of upward sloping tangent line, which means we're going to have a derivative that's positive because it's upward sloping. So we put in our function, we put in our differentiable variable x, and we evaluate it at 3. So the older calculator here is our function, our differential, and our evaluating at 3. And then when we hit enter here, we get a derivative of 6. So in other words, our curve at that location is sloping up 6. So that's just kind of a refresher to using the Math 8 button. And then just a word of caution. Let's go back to functions that have a point of non-differentiability. In other words, we have a location where we can't take the derivative. If we plug this into our calculator, so we're going to do our Math 8, we know the derivative doesn't exist here. We know that we have a corner here, and we have 2 different slope values coming in. But if we put this into our calculator, to access your absolute value, that's going to be a math number 1. So you're going to go into your calculator, and you're going to hit Math 8 to get your derivative. And then you're going to go back and you're going to put your x here. And then when you come into here, you're going to go back to your math key and hit math, and then arrow to the right to get number, NUM. And then you're going to choose option 1, which is absolute value. And you're going to put in your x here. And then we're going to evaluate it at 0. Okay, and then if we got the older calculator, it's the same key sequence. You just have to remember to separate it with commas. So we know it doesn't exist, but what's going to happen is when we plug this in and hit enter, our calculator is going to give us a value of 0. And the reason why your calculator is doing that is because your calculator is numerically determining the derivative, and it's taking a point on this side and a point on that side of the corner, and it's getting closer and closer to the corner. And since it's taking points that are symmetrical about the corner, if it starts out here, it takes this point and this point. If you connect symmetrical points about that corner, you're going to get a slope of 0. So it's incorrectly estimating the derivative by taking slopes closer and closer and closer. And so your calculator isn't smart enough to realize that there's a corner there. So this is where you have to be smarter than your calculator. And that's why it's a good idea to be able to get a picture of what the absolute value of x is, so that you can find those corners and cusps and things like that, which is why we do our function aerobics in class. That's why I make you do your absolute values and your x squareds and all that stuff to get that physical picture of that function. So this whole page is getting you to think about being smarter than your calculator. Okay, the other way to calculate a numeric derivative. So we're going to still stick with x squared. We're going to use x squared a lot, and we can also use our grapher. So you're going to go into your grapher, okay, and so we're going to go and set up our functions. So we're going to put our function x squared into the first grapher register y1, and then we're going to go down to y2, and we're going to hit our Math 8 key to get our derivative. So it's the same process on either type of calculator. And the difference here is we're gonna get our differential x and our function x squared and our differential x again to tell our calculator what variable to look for in here. And then instead of putting a numeric value at the end here, we're going to just put another variable x. So if we notice the syntax for the older calculators, it's x squared comma x comma x. So that last entry, which we used to put a number in, what that last entry does is it tells the calculator, do the derivative for every value of x in the domain. So if your grapher is going from an x value of -10 to an x value of +10, it's going to put in every value between -10 and +10, and it's going to find a numeric derivative. And then it's going to plot each one of those points. So that's how we can plot the derivative point for point. So after you get this in y1 and this in y2, then you can go ahead and graph. And you'll see the function here in blue, and you'll see its derivative here generated in red. So notice y2 is the derivative, okay? And so we can look at this. So now I'm going to ask you to use your trace key and select the derivative. So use your up and down arrow on your arrow pad to select the y2 function, and use the left and right arrow to trace and look at these values. And as you trace this derivative function, what you'll find is that there's a relationship between the x and the y values, and we see that the y values are always twice as big. So we know this is a line, and its intercept is 0, and its slope must be 2. And so we can come up then with an equation for the derivative. The derivative f prime of x, so working with our notation here, remember function notation is f of x, and we use the prime to signify a derivative. So our derivative must be 2x. So if you notice, our function, our original functions is a function, passes the vertical line test and all that cool stuff. Its derivative itself is also a function. We'll pass the vertical line test and all that cool stuff. So when we differentiate functions, we get more functions. So kind of keep that in mind as we go into the next section. So there are two theorems in your notes, and we're just going to mention them briefly, and they're written kind of unusually complicated, but they're kind of getting at just this basic thing about derivatives. So don't read too much into it. So if we think about being able to calculate a derivative at a, so let's think about our x squared at 0. Okay, and we know the derivative of x squared at 0 is 0. It's where the vertex is, and we know the tangent line's horizontal at the vertex. If we have a derivative, then the function has to be continuous at that location. So if we can calculate a numeric derivative, then we know we have continuity. We know we have a continuous function. So that's kind of what we're implying here by this theorem. So implying that we can calculate a derivative means the limit exists, it's continuous, it's smooth. That was our definition of derivative. And so we can see then we've met the continuity requirement. The next theorem has to do with the intermediate value theorem, and we had an intermediate value theorem in chapter 2 for functions. And this is basically saying the same thing about the derivatives. And that is that if we have this function and we can find a derivative at 2 locations, so we find a derivative at point A, and let's just call that a half. It looks like it has a slope of about a half. And we can find a derivative at point B somewhere else. Let's call that 3 because it looks steeper. I just made up the values, just kind of estimated them. Then what we're saying is if at A the derivative is a half, and if at B the derivative is 3, then if I pick a point in between A and B, I've got to have a derivative in between a half and 3. So and if you remember back to the intermediate value theorem for functions, that was the same thing. So in other words, they behave much like the number line behaves. So this derivative here, because it's between these two values physically, must be between these two values numerically. So if we turn this into a multiple choice question, then the derivative can't be 0 because 0 is not between a half and 3. The derivative cannot be -2 for the same reason, negative a half, excuse me, because negative a half is not between a half and 3. And I'll skip over C because C is the correct answer. The derivative can't be 4 for the same reason, because 4 is not between a half and 3. So C has to be the correct answer. This derivative has to be 1. That has to be the possible correct answer because that answer 1 is between a half and 3. So it's exactly the equivalent to the intermediate value theorem for functions. So if we just go over our essential question again, when does the derivative fail to exist? We're gonna have what you need to do is you need to get that visual picture of corners, cusps, vertical tangents, and jumps, or piecewise functions, where they transition. You need to get the visual picture of those 4 scenarios in your mind, so that you can see where that derivative fails to exist. At this point, you're ready to start the day 1 homework. Like I said, section 3.2 is just 1 day, So we're moving on to section 3 tomorrow.